So in this video, we're going to get into a little bit of the math regarding equilibrium. So equilibrium systems are going to be defined by concentration. And so previously I discussed about the concentration of the sodium chlorides in this situation and talking about the concentration of these things at equilibrium being constant. And that's going to be something that follows through this whole unit. Concentration really is vital to understanding equilibrium. So at equilibrium, a concentration amount in mole per liter or millimole per liter will be unchanging at equilibrium. So this is represented frequently in equilibrium graphs, and I love equilibrium graphs. They're going to come up frequently. And if we look at this equilibrium graph, we can see that the hydrogen gas starts out and it's getting used up, and then it flattens out. And the quantity here is going to be a concentration. So mole per liter or millimole per liter. And then for the iodine is getting used up and it flattens out at the same spot. Now you'll notice that they have a 1-to-1 ratio of hydrogen and iodine, but they started at different points here. But they're getting used up at the same rate. So the slope of those graphs are kind of in parallel. As a little hydrogen's used up, the same thing happens for iodine. But the hydrogen iodide here is at a 2-to-1 ratio. So when it starts off, you can see that there was some hydrogen and some iodine. They're getting used up, but there was no hydrogen iodide. But then it's getting produced at twice the rate that the hydrogen and iodine are being consumed. Now, at equilibrium, we still have some of this hydrogen, some of this iodine, and we have the hydrogen iodide. So we haven't used up all of the hydrogen, we haven't used up all of the iodine. This wasn't quantitative, but we have a constant concentration of those two things at the equilibrium. So at equilibrium, those are our concentrations of the three chemicals in the reaction. Now, ICE tables are super useful. And what the ICE stands for is initial change in equilibrium. And so the ICE table is going to follow the change from the initial concentration to the equilibrium concentration. And this change step is going to be our stoich step. So that's where the stoich occurs in this, is in the change system. So ICE tables only work if you can calculate the amount concentration or mole per liter or millimole per liter. This includes gases, because gases you could have mole per liter. You could have mole per liter for aqueous solutions or solutions in different solvents like alcohol or cryolite or some other thing that you've dissolved. So if it's a solution or a gas, we can use that to find amount concentration or mole per liter or millimole per liter, but we do not use the mole per liter for pure liquids or solids. So if something is a pure liquid or a pure solid in the reaction, it is considered a constant and it doesn't come into the ICE table. We don't include it, and we will not use it later when we're calculating the equilibrium constant. So let's do an example here. I've drawn an ICE table for us already, but let's consider the reaction or the reaction equation for the formation of hydrogen iodide at 48 or 448 degrees Celsius. Now, the temperature is listed. It has no direct bearing on our calculation, but one thing you need to know is the equilibrium position is dependent on temperature. So equilibrium position is only really dependent on temperature and the kinds of reactions. So other things that we do to it will not actually change the equilibrium constant, but temperature does. So we're going to assume the reaction has begun with 1.00 millimole concentrations of hydrogen and iodide, and then we're going to have the equilibrium concentration of iodine is 0.22 mole per liter. Now it says determined by color intensity. Iodine is a red-brown color, and so the more concentrated that gas is, the darker it appears. So if they shine a light through it, they can actually figure out how concentrated the iodine gas is. So that's what that means. So let's write our reaction first of all. So this is formation of hydrogen iodide. So I've got hydrogen gas plus iodine, in this case gas, is in equilibrium with hydrogen iodide gas, and we get 2 hydrogen iodides to balance it. Now, my hydrogen gas is going to go here. You can see our units are millimole per liter, so we're going to have millimole per liter, and I don't have to write my units in every box. And then I get hydrogen iodide in millimole per liter. And if you want to write 2 here, I'm okay with that. So my initial concentration of hydrogen and iodine is 1.00 millimole per liter. So if I'm starting with only hydrogen and iodine, my concentration of hydrogen iodide is 0. We don't have any. We've just put hydrogen and iodine into the container. It also tells us that at equilibrium, the iodine has a concentration of 0.22 mole per liter. Or, sorry, I don't need to actually write the millimole per liter because it's units been given. So now, this is all of the information that's been given, but what it wants is us to calculate what this value is and what this value is. So what I'm going to do now is I'm going to find the change and use the change to calculate the other things. So here, I went from 1.00 to 0.22. That means I have used up the difference between those. So if I take 1.00 minus 0.22, I get 0.78 has been consumed. So that's the amount of change, right? So that change of the iodine is going to apply to the other things because the change is the stoichiometric step. So if I had used 0.78 millimole of iodine, I can multiply by 1 hydrogen for every 1 iodine, and I'm using the coefficients from here to calculate the amount of change here. So this is minus 0.78, and this will also be 0.22 millimole per liter, which makes sense. I started with the same amount in this situation. I had 0.22 of this, so I'm going to have the same value for the other reactant because it's a 1-to-1 ratio, and I started with the same amount. But when it comes to the hydrogen iodide, this is a stoich step. So I'm going to have 0.78 millimole per liter, but I get 2 hydrogen iodide for every 1 iodine. So I'm going to get twice as much of that changed. So this is 1.56. But there's another thing here. In the reactants, we had the reactants were being used up. That's why those are negative numbers. If I'm using up the reactants, I am making the products. So when on the other side of the equilibrium arrows, this becomes positive. It's going to change by a positive amount. If I'm using up reactants, it's going to make products. If I was using up products, it would make reactants. So 0 here plus 1.56 is 1.56. And that's how you calculate the use an ICE table. You're going to get told how much the initial amounts of things are. They're going to give you one of the equilibrium values, and then you have to populate the table. You find the change, use stoich to get the other changes, and then apply it. Now, this is here it's got percent yield. So when we talked about the position equilibrium, is it greater than 50%, less than 50%, stoichiometric, we need to know how much product there was made. So here we've got 1.56 or 1.6 millimole, And the most we could have made of this is if I took this and made the product, it would have made 2.0 millimole because it's the 1.00 at a 2-to-1 ratio would have been 2.0 millimole. And this would have made the same amount. So your theoretical amount would be 2.00 millimole. And so this is 80% of the possible product was produced. So that's our percent reaction. And we can see that that's greater than 50%. So it favors the products. Okay, so I'm going to get you to try to fill in this table and see if you can populate it. In the first example, you've got 1 and 1. This is a 0, right? So we're assuming that when they're starting off, this is going to be a 0. And give that a whirl. See